So the carbonyl compounds are those organic compounds which contain the carbonyl, that is C double bond O functional group. Now you have two types of carbonyl compounds. Okay, so the two types are like one is your aldehyde and one is ketones. So aldehyde and ketone. So as far as aldehydes are concerned, those compounds that have carbonyl at the end of the carbon chain. Okay, which means that on the right side, okay, on either side, hydrogen will be attached with the carbonyl group. So carbonyl is attached at end of chain. So it will be like you have R, then you have carbonyl group, and then you have one hydrogen attached to it. Okay, that is how we identify the aldehydes. So we have some examples like how do we name them. It would be for example, if I take ethanol, ethanol will be, you have one side new basically needs, ethanol means two carbons, so it will be CH3 C double bond O and H. So you will be writing it like CH3 CHO. Okay, then you have propanol. Okay, I'll just write one more. You should be aware of the namings of aldehydes as well as ketones. So CH3 CH2 CHO, that is your propanol. As far as ketones are concerned, the carbonyl group is attached inside carbon chain. So it is basically does not have any hydrogen with it. It will be like this carbonyl group, and then again you have the carbon chain on the other side as well. So it is like ethanol. It will, now we will call it ethanol, or oh sorry, basically there won't be any ethanol, right? Because we cannot make, with two carbons we cannot make a ketone. It will surely have a hydrogen. So our ketones will be starting from propanol. So it will be like CH3 CO then CH3. Clear? And the isomers will be starting from pentanone. Okay, butanone will not have isomer. If I'm, yeah, correct, it will be having, yeah, so it will be only 2 butanol, but we will call it butanol. The isomers, the positional chain isomers or the positional isomers will be starting from pentanol. So it will be like, we will have pentane 3 on, so it will be like CH3 CH2, then CO CH2 CH3. Okay, but if we move it to the third side, it will be then the different naming. So you have isomers will be starting off from the pentanol, carbon number 5 of ketones. So you have these two carbonyl compounds. Okay, as far as some properties are concerned, physical properties, because for every carbon organic compound we have studied the physical properties. So if we consider, hmm, first property could be again the boiling point. So boiling point of carbonyl compounds is basically higher than alkanes. Okay, like ethane and ethanol. Ethanol will be higher, okay, in boiling point. Why is that so? Because ethane only have ethane and you have ethanol, that is CH3CHO. So this only have temporary dipoles. Okay, they have weak van der Waals forces. But as well, if we consider ethanol, it also has permanent dipoles as well. Why? Because of the carbonyl compound. This will have negative and partial, okay, positive. So it considers it will make dipoles. So you have an extra force, that is why it will be having more, boiling point compared to its respective alkane. Clear? And what about solubility? So carbonyls will be soluble in water. Why? Because they can again form hydrogen bonds like the ones we saw in carboxylic and alcohols. Can form hydrogen bonds with water. Okay. So if we consider the preparation of carbonyl aldehyde and ketones that we have already studied, okay, in alcohols. So for aldehydes, if you remember, that was we had to distill it. Say okay, the aldehyde formed must be distilled off as soon as possible. So that if we don't okay distill it, it will become a carboxylic after further oxidation. That was one thing. Apart from that, to make ketone, we were doing. Let me just show you. Okay, product is distilled as soon as possible. Aldehydes are formed. Now, how the aldehydes are formed? You can see reagents we were taking acidified K2Cr7 or KMnO4 and heat under reflux. So if you are taking a primary alcohol, that will make a aldehyde. So the two hydrogens are separated, okay, and carbon forms a double bond with the oxygen. And for this one, you can see alcohol is limited, then it further oxidizes to carboxylic acid. For secondary alcohol, we just do heat under reflux, so there's no further oxidation, it will directly form a ketone only. Okay. Okay, so now we have reaction of aldehydes and uh, ketones, basically reactions of carbonyl compounds. So first we discuss the reactivity, okay. So the carbonyl compounds contain the carbonyl group, okay, that is highly reactive. Why is that so? Because we have partial charges induced on it due to oxygen. Okay, oxygen is electronegative atom. That is why it induces partial charges, negative partial on itself and positive partial on the carbon. So now it is a nucleophile. Nucleophile is the one that is always looking for a positive region, for a positive carbon or for any positive element. Okay, it is always looking for it. So when it sees, okay, when it detects carbon with a positive partial charge, it will attack this carbon, and then a sort of reaction happens and it gets added to this, the whole compound that will be. So basically this will be nucleophilic addition. Okay, that what are you doing? That you are adding a nucleophile in the compound. That is what we call nucleophilic addition. Clear? Okay, but first we will be looking into yes, double bond. Yeah, this is the just an explanation I have given. Okay, I will draw the mechanism. Okay, this was just a logical explanation. I have not made the notes of it right now. Okay, but before nucleophilic addition, what we need to study is two reactions that are basic. Then we will move on to the one that has nucleophilic addition. So first is your reduction. another is your oxidation. The both reactions we have already studied, but just in case I will write it here also. So for reduction, the reagent conditions, products, reagents will be lithium, okay, aluminium hydride, that is tetrahydro, what do you call it, lithium tetrahydroaluminate, okay, tetrahydroaluminate, but you can just call it lithium aluminium hydride. So okay, there is no need to call it with along with its actual name, that usually don't come. You have just have to write the molecular, so the chemical formula. Either you can use this or you can use sodium boron hydride. These are two reducing agents, strong reducing agents, okay, and they provide the H is your basically here the nucleophile. So the mechanism is same, the mechanism is nucleophilic addition that is happening, but for this reaction the examiner will not ask you to draw the arrows and etc. The HCN reaction that we'll study at last, that will be in which the arrows and the dipoles were etc will be have to be shown. For that you only have to remember it. So you are using lithium aluminum hydride, sodium boron hydride, and for remember for lithium aluminum hydride the condition will be in dry ether, because if you don't use dry ether then what happens, the lithium aluminum hydride gets reacted, okay, it becomes much stronger. That is why we, to reduce its solubility, we use dry ether. And then you have sodium. For sodium the condition will be aqueous alcoholic solution. Have to remember these two conditions. Clear? Apart from this, what will the products? The products depend on the type of reactant you have used. So if you have used aldehyde, if you are reducing aldehyde, and if you are reducing ketone, if it is aldehyde then it will form primary alcohol. So it is basically a reverse process. And if you are forming using ketone, then it will form a secondary alcohol. Clear? So if I'm taking example, ethanol, to ethanol, it will be like CH3 CO and you have H on this side. You are adding hydrogen because this time you're reducing, okay, reduction is being done here, so it will form CH3 C. Now you'll be adding 2H here, okay, the 1H is already placed here. 1H will be for the OH and 1H will be for the another to complete the valency of the carbon. So now you have formed because primary alcohols have two hydrogens with it, so you have to place another H here. This will be two hydrogens. That is how you will be forming the ethanol. And if we take propanol as example, ketone, and we want to form propan-2-ol, plus hydrogen reacts to form CH3C. Again you have CH3 here, you have your O here, and now you are adding hydrogen, one hydrogen here and one hydrogen here. Okay, so this forms propan-2-ol. Very basic and very simple reaction. That is a reverse of the oxidation that we have done in alcohols. Then you have oxidation. Okay, for oxidation only the aldehydes will be oxidized. So I'll not go into the detail because we have already studied that in our alcohols chapter. I'll just write here that aldehydes oxidizes to carboxylic acid, and ketones does not further oxidize. And note will be covered in detail in alcohols. Okay, clear? Then you have third reaction, that is reaction with HCN. Hydrogen cyanide. So what usually happens that you're taking the reagent, let me just write it, reagents condition product. So reagents will be it will be sodium. Okay, you can take NaCN and along with that sulfuric acid. Okay, and along with that you will be taking the room temperature as condition, because carbonyls are already reactive, so they don't need heat under reflux. And what we are making here, we are making hydroxynitriles here. What are hydroxynitriles? Those compounds that have OH, hydroxys or OH group, as well as nitriles, that is CN group. Both groups in their compounds, that we call as hydroxynitriles. Okay, but in the heading I have written that we are using HCN. So why we are not using HCN as directly a reagent? The reason is that HCN is a poisonous gas. Okay, so we only produce it during the reaction between NaCN and sulfuric acid. Then only the HCN is produced, and then we use it for the reaction. We don't store it, okay, and we don't, because it is a poisonous gas. Clear? So if we take a basic equation, first for an aldehyde. So what happens that if you're taking an aldehyde like this, and then you are adding HCN in it. So it's quite simple. What usually happens here is that H O is here, then you have just keep the hydrogen that was already there. I have placed it on the downward side. What happens that H will go to the hydrogen and the cyanide group will attach be here. That is how we are forming a hydroxynitrile. So the what will be the name of it? Can you guess the name? We used ethanol. Hmm. So first consider the carbon chain. Now the carbon chain is of 3. Okay, how do we pronounce this? It will be propane nitrile. And on propane nitrile we have OH, okay, the hydroxy compound on the second carbon. So it will be 2-hydroxy propane nitrile. Clear? Then for the ketone, same concept will be applied. CH3, CO, CH3 plus HCN. Now what will happen that CH3 C, and then you have CH3, H will be placed here and the cyanide will be placed here. Now what will be the name of this compound? First take the carbon chain that have cyanide with it, and then consider the name of it. Hmm. So you have this chain, it is propane nitrile. Then on the second carbon you have two things. You have a methyl group as well as you have a hydroxy group. So it will be 2-hydroxy 2-methyl, okay, and then propane nitrile. Clear? The mechanism for this reaction, that is nucleophilic addition, we will study it now. So I will write it, the carbonyl group, that is CO, makes carbonyl compounds reactive, inducing partial charges due to electronegative oxygen. So the carbon becomes more, I would like, susceptible to the attack by nucleophile. So the basic concept is like this: you have carbonyl, partial positive, partial negative, nucleophile. So it attacks, okay, the carbon with partial positive. That is why this leads to nucleophilic addition. Now what happens, the mechanism? First you have what we can take is like, yeah, we can take any ketone here, propanol for example. Let me just write hacking mechanism. First you have a ketone CH3 C, let me just write it like this, CO, and you have CH3. Okay, now this CH3 and will have first the partial charges. Okay, that is very important, due to which the reaction is happening. Now the first arrow will be from middle of the double bond to the oxygen. This is your first arrow. Then in the same compound that we have drawn currently, a nucleophile, which nucleophile? The cyanide. Okay, do show its lone pair and the charge of it. The arrow will be from the lone pair, okay, and now it will be towards the carbon double bond, towards the oxygen. After that, second step, what happens? You have CH3 C, one CH3 was in the downward side, or we can place it upwards, okay, because the thing is that cyanide is coming from down, right? So we have to shift it upwards, and your oxygen has taken the both electrons, so it will be having lone pair along with a negative charge, and cyanide will be attached here. Okay, clear till now? Then after this, what happens? We take this intermediate that we have formed, and now the hydrogen we have to basically consider the hydrogen. Okay, remember this cyanide that we have taken, this cyanide is from NaCN, not HCN. Okay, the nucleophile that we are taking is from NaCN. Why is that so? Because NaCN provides a stronger nucleophile compared to HCN. That is the concept. Remember this. Now what happens? Yeah, that yeah. Both are same because both are group 1 elements, group 1 metals, right? So you can take any of them. Now what happens? You brought HCN. Okay. Now HCN, this arrow from middle will go towards cyanide, this one, and this arrow from the lone pair will go towards this hydrogen. And let me just make a little bit of space here. So now you have hydrogen here placed here, you have cyanide placed here, and the byproduct will be the cyanide, okay, nucleophile again. Okay, so I hope it's clear. Yeah, stronger nucleophile. So this is your two-step mechanism. This is one step, but we show it as two. Then, okay, do remember the oxidation, reduction, as well as this, the third reaction that we have done, all follow the same nucleophilic addition mechanism. Okay, behind the mechanism is nucleophilic addition, but the type of reaction is changing with its name. Is it clear? Then you have final topic of test. That is a really important topic, aldehydes and ketones. So first, the test number 1 is using 2,4-DNPH. Now what is this? 2,4-DNPH is, you should be able to remember this name, okay? That is, on carbon number 2, 4 we have dinitro dinitrophenyl hydrazine. So if we see the looking at the structure of this compound, we have a benzene ring, let me just draw a perfect circle. Okay, then on carbon number 2 and carbon number 4, so you have like carbon number 2 here. First I draw the carbon number 1. On carbon number 1 you have hydrazine. If phenyl hydrazine is NH, and along with it you have NH2. Now on this is your carbon number 1, okay? So carbon number 2 will be this one. On this you have a nitro group. Nitro is NO2. Okay, till now you just have to remember this formula and the structure. You will be studying this in detail in the A2, okay, in your A2. And you have on carbon number 4 NO2 again, so it means they are dinitro. Okay, so this is the formula for 2,4-DNPH. So what are we using? We are using this to test the presence of carbonyl group. Carbonyl group is in both aldehyde and ketone. Test is used to check the presence of carbonyl group, that is CO. Okay, so both aldehyde as well as, this is the test that is used to check carbonyl compounds and distinguish them from other organic compounds. So in carbonyl you have both aldehyde and ketone, both will react with it. Okay, but we are not using 2,4-DNPH as alone, okay, as a single. We are making a Brady's reagent. We call it a Brady's reagent. Okay, so we use Brady's reagent, that is the mixture of 2,4-DNPH plus you have some methanol in it, plus you have some sulfuric acid in it. Okay, that is make up a whole reagent that will be using here. Clear? Okay, what will be the observation? The observation will be observation of test, it will be having a orange, yellow precipitate, or you can directly write orange precipitate. So you will be getting an orange yellow precipitate. So if we look into the reaction, okay, do remember the type of reaction that is occurring here, and that is condensation reaction. So it will be like, if you are having, let me just draw simple, R, then CO, then R. Okay, because we are not concerned with the R, we are just concerned with the carbonyl group. Then you have NH2 here, NH, benzene ring, and nitros here. Okay, this is our structure. Then what happens? This O gets separated with one of its H, oh sorry, both H, so okay, H2, and it forms water. So the final compound is like this. Double bond with NH, sorry, with N, then you have NH, like this. Nitro here and one nitro here. That is a compound. And along with that, why we were saying that it was condensation? Because along with that you are getting a water molecule. That is why. Again, any reaction in which a water molecule is being formed, that will be your condensation reaction. Clear? So in the test tube you will be seeing an orange yellow PBD that looks something like this. Okay, this is your whole reaction of the first reaction, that was 2,4-DNPH, that is used to check the presence of carbonyl, so which means both aldehyde and ketone will be reacting with it. Now we will see the two more tests in which only aldehyde will be reacting. So that is used to distinguish aldehyde from ketone. The first one is your tolerance reagent, that is a silver mirror test. Tolerance reagent, or we call it silver mirror test. In silver mirror test, what happens that tolerance reagent is basically diamine silver ions. Okay, diamine silver ions are complex ions. You will again, okay, you will be studying complex ions in A2. So you till now you just have to remember the formulas of it. It is having diamine silver 1 ions. So they basically look like this: Ag NH3 2 and on the outside you have plus, because this is whole a complex sign. Okay, so it is a charge on the outside. Okay, so what usually happens, that aldehydes will be getting oxidized. Okay, basically this reaction is oxidation. So you already know that aldehydes get further oxidized, ketones cannot further oxidize. Okay, so they will reduce these diamine silver ions and will get oxidized by, okay, themselves. Aldehydes reduce these silver ions and itself gets oxidized. Ketones won't react, as cannot get further oxidized. So what happens, that observation will be, it will be a gray precipitate, or you can say a silver mirror is formed. Okay, so we have written observation. So if we add an aldehyde here, so what happens, a silver mirror formed, or what are we seeing in gray precipitate. But if we add ketone in this tolerance region, you will see no change. So silver mirror usually look like this. Okay, this is a silver mirror sort of concept. Okay, then I don't think so you need to remember the equation. Have you done the equations of these reactions in your class as well? No, right? Because they usually don't give you the equations. But I'll just paste the equation for your reference. Okay, so that so you have taken an aldehyde, then you have taken the complex ion, then you have taken water. Okay, that OH minus. When you heat the reaction, you get Ag, the silver mirror, that is the, okay, observation that we are seeing. Then you are getting ethanoic because you are basically oxidizing it, and along with that you are getting ammonia as well as water. Okay, then you have Falling's solution, that is the third test. In Falling's solution, it contains copper 2 ions basically that are complexed with tartarate ions. So it looks, because we have not we will just get the copper to wines. Okay, Failing solution contains complex copper to wines. Okay, so what happens that again oxidation is okay being done here. Basically the reaction on the whole is a redox reaction, because both the tolerance and the Fehling solution, both the reaction redox, because aldehyde is getting oxidized, and the reactant that we were using, the solution like Fehling solution that we are using, that is being getting reduced. Okay, in that copper, basically the copper will be getting reduced to copper plus, so that is a redox reaction on the whole. So the observation of this test is basically red precipitate is observed. Observation, red precipitate observed. And apart from this, again, if I show you one example, the equation. So the red precipitate is actually of the copper 1 oxide, okay? That is, you can see in the Cu2O, that is copper monoxide. So copper was reduced and again the ethanol was oxidized. Okay, clear? Then what is left? We are now left with iodoform test. Iodoform test is left here. Let me just cover that. So iodoform is basically for, I would say, both the alcohols as well as for the carbonyls. Okay, iodoform test is basically used to detect, basically what were we detecting? We are detecting those carbonyl compounds that have methyl group at the end. Okay, so basically, like methyl ketones have CH3 on one side, then it has carbon chain on the other side. So first I will write used to detect compounds having methyl groups. CH3 on one side of compound. So as far as your aldehydes are concerned, aldehydes, only one aldehyde will pass this test. And which one is that? Ethanol. Why is that so? Because ethanol only have, okay, ethanol is the only compound which have CH3 on one side, because you have the functional group, and alongside with the functional group you have to see the methyl group. Clear? Because after that propanol will be having CH3 CH2, then the chain increases, because we cannot make CH3 here, we have to make an aldehyde, so the carbonyl will always be at the end. So only this aldehyde will pass this test. Clear? And what about ketone? Ketone usually starts from propanol, right? So for ketones we have multiple examples like this. Many ketones, we usually call them methyl ketones. Pass this test. Okay, what is being done in this test is, you are taking the reagent. I will be writing the reagent. Reagent is iodine I2, that is why we call it iodoform test. Iodine along with NaOH aqueous, that is our alkaline, so okay, solution. We are making an alkaline solution of it. Then what happens at the first? Let me just draw it here. Or should I show you the equation? Okay, I'll just show you the equation. See the equation. In the first step, what is being done here, you have an aldehyde, the ethanol, as a basic, okay, the only aldehyde that will react. So what is happening, that I2, when you reacted I2 with it, the first reaction that is being done here is halogenation. All the H that were there got replaced by iodine. Okay, then after that, in step 2, you added the alkaline NaOH aqueous to done the hydrolysis. What we mean by hydrolysis, that we are breaking the compound. How we are going to break the compound? We will be breaking the compound from here. So the CO you can see here, and one more oxygen we have added here with Na plus. Along with that, this Ci3 got attached to an hydrogen and it formed CHI3, that we call as triiodomethane. Triiodomethane is the thing that will be giving you the observation, the yellow precipitate, yellow color. Clear? You just need to remember the equation, how the salt is being formed and all that. So this was our whole reaction. The same is usually applied for I would say alcohols as well, because we have seen the questions if you remember. So the alcohols were also following the same iodoform test, because in the end alcohols usually get oxidized to aldehyde as well as ketones. Okay, reagents, equations done, and observation. Yellow PPT. Okay, apart from this, we also have just one more small topic of nitrogen compounds. Nitrogen compounds is in detail in your, um, I would say A2. Okay, so it is not in detail, that much detail in this ES. It will be coming more in detail in A2. Nitrogen, then you have phenylamines and all that. So that is a very detailed topic. Okay. So let me just see what is left. Okay, let me do some past papers. Okay, we can do some past papers of it. Okay, do question number 1 and 2.